Right. Welcome everyone to this week's Physics Meets ML. We are very happy to have Siamak Ravanbaksh today. He is a Cypher AI chair at McGill, and he will tell us today about a lot of his recent work in the context of symmetry, and his talk is entitled Compositionality of Symmetry in Multilayer Perceptrons. And please feel free to ask questions at any time. Yeah, the floor is yours, Siamak.
Thank you very much, and thank you, the organizers, for inviting me. Yeah, so I'll talk about compositionality of symmetry in MLPs. This is the outline of the talk. I will first give a broad background on representation learning using symmetries and equivariant MLPs, how to build them, and then I'll look at 4 ways of using compositionality and the utility of these different compositions in building equivariant multilayer perceptrons. One is the direct product, and then I look at diagonal action of the groups and their utility in getting universal layers. Then I'll look at leaf product and its application to building models for hierarchical structures. And finally, I'll talk about block systems. That's a generalization of some of the other types of composition. Okay, so first, we want to understand what are the equivariant MLPs. So we start with symmetry. As many of you know, everyday notion of symmetry is defined through a set of transformations. So we have a set of transformation calligraphic T, and we say some object is symmetric if the transformations of that object leave that object invariant. In the context of representation learning, we're looking for functions f that map our observations to some representation space. And in order to learn this function very quickly using the data so that we are data efficient and we generalize well, we use some sort of inductive bias. And one inductive bias that we could use is invariance to symmetry transformations. So the value of this function f does not change under the transformation of the. But then this type of representation is not ideal because it's discarding information about the transformation T. One way to do better is to parameterize these transformations, for example, using a set of parameters theta. And then this better representation has this invariant part like we had before. But it also has a second part that encodes information about transformation or pose of the data. So you see an example here. We're transforming the input objects. We have some part that is constant as we transform the object, and some other part that changes by the transformation. This is one specific manifestation of equivariance, and in order to define this more formally, we need groups. So the reason that group theory comes in is that these transformations that we're looking at, the ones that they actually form a set, they compose with each other, and they're usually invertible. And so their compositional structure forms this is abstract. And to understand this distinction of the actual transformation and its compositional structure, you can look at this example where in one case we have an object and we're changing the lighting of the object by using 3D rotations of the lighting. In the other case, in the other example, you could assume that we have same type of object, but now we are rotating the object itself, again using 3D rotations. In both cases, the composition rules are the same. but we have different transformations. So the abstract underlying group is the SO3, but the transformations are different. And so we can formalize this notion. So we start with the definition of a group. We say group is a set with a binary operation. So we have a group G, the set of elements, lowercase g, such that they compose with each other, and the set is closed under the composition. We have associativity. We have an identity element and a unique inverse for each element in the group. Now, once we've defined this group, we could say the transformations T are parameterized by the members of the group. And these transformations satisfy two conditions. One is that the transformation corresponding to the identity element of the group is the identity transformation. And the second constraint on T is that the transformation corresponding to the composition of the group members is equal to the composition of those transformations. And so once T satisfies this condition, we call T the action of the group G on set X. And we call X a G set. And moving forward, rather than writing TG of X, I'm going to write G dot X. So this means that X is being transformed using the group number G. A special type of action that I look at is the permutation action. Here, like this type of action is useful if you're looking at the transformations of a finite set of elements, or we're looking at finite groups. We can often encode the transformations of those finite number of elements, like the variables, using permutation matrices. So this group action now can be written as the multiplication by permutation matrix row for each element G. Example of this is translation of pixels, right? Where if we translate this image, for example, assuming circular boundary condition, we are shuffling the pixels using some permutation. Okay, now we're ready to define equivariance. So we have some input X coming from the G set, and we're transforming it using G, and then we are producing the embedding or representation f of G dot X. And an alternative route to the same result, so to the similar result, would be to first create the representation and then transform the representation. And we say that this representation is equivariant with respect to the group G if these two give us the same results. That is, transformation of the input has the same effect as transformation of the output. Now here we can have different actions on input and output, but in a lot of applications that we look at, these are the same. And we are interested in cases where F is an MLP. It's a multilayer perceptron. The question is, how do we make F satisfy this condition? So this condition is imposing a constraint on F. It's a strong inductive bias, and we're interested in imposing these on MLPs. A sufficient condition for this is to make each layer equivariant. And so we can look at this condition now, making just one layer equivariant. We have the group acting on one feed-forward layer, where we have a weight matrix multiplied by the input of the layer, and we have the nonlinearity. And we want this to be the same as when we transform the input. And so, because we are looking at permutation groups, I can replace these two actions by permutation matrices. They could be different permutation matrices, right? And because if we're dealing with permutation matrices again, sigma is a bijection, I can get rid of the sigma. Because the equality holds here for every x, I can get rid of the x, and what I'm left with is a symmetry constraint on W. So This is a symmetry constraint on W. We need this to hold for every G. And this is always going to lead to parameter sharing in W. Okay? Now we'll see shortly why through an example, but because these are permutation matrices, and this condition is basically making sure that all the elements of W inside one orbit have the same value, we always get parameter sharing. So this same equivariant linear map can be expressed using group convolution. So there is a one-to-one map between the two. And this is the language of group convolution is the one that is also used a lot in equivariant deep learning. And this, while this is for finite groups, for permutation actions, a similar constraint can be derived for classical D groups, as is done in Finzi et al. Recently. Okay, so let's see an example. So if we have the input X, that is this sequence, and we translate the input, we want the output to be translated. So the group is the cyclic group of order n. So we want the translations to result in translations. And this means that the parameter matrix W should have this type of parameter sharing in it. And the way to actually construct this parameter sharing is very simple. You start with one element of this matrix and see the orbit of this element as we apply the group, each group member to the input and output. So this, if we translate the input and translate the output at the same time, we're gonna create this orbit. And so we're gonna tie all the parameters in the same orbit. And we're gonna do that again and again. We end up with this parameter sharing matrix. This process of finding the orbits in the parameter sharing in this matrix can be done very efficiently in the order of the size of the matrix times the generators of the group. So it does not depend on the size of the group as it is claimed in some recent papers. This can be done very efficiently. So this gives us a computational method to basically find the parameter sharing matrix for finite groups. Here's another example. This is the symmetry group now. We want any shuffling of the input to result in the same shuffling of the output. In this case, we get a two-parameter model. And as is the case with many other examples that we see in the talk, we can efficiently implement this linear map using pooling and broadcasting operations. So I'm going to go over this because we see this again. So this multiplying this matrix by a vector can be written as first multiplying each element with W1, then doing a pooling over all the elements of the input, multiplying by W0, and broadcasting them. And this means that this operation has a linear time implementation. And here, while we have two parameters similar to convolution, we can have multiple channels, and so we can build very expressive deep models. Now that we know what equivariant multilayer perceptrons are and we know how to build them, let's look at different types of compositionality. So the first one is direct product. What I'll do is that as I go through these examples, I'll first give you, I'll go through these compositions. I'll give you one example first to motivate it, and then I'll talk about the general case. So the example that we see here is when we want to look at interacting sets. So we have a set of patients, set of genes, and we have the gene expression data for them. The symmetries in this case is that I can shuffle the patients and genes independently. So I have a symmetric group Sn and Sm acting on these two sets, and I'm modeling the interaction of these two sets. Suppose I want to predict some of these missing gene expressions, or I want to predict something about patients. How do we build a deep model for this? Now this has many other applications. You want to model object force, or you want to look at higher order interactions. You see that it's a similar principles apply. So here we have a direct product of groups acting on the Cartesian product of sets. So what we show is that the parameter sharing matrix, in this case, has 4 parameters, 4 untied parameters. But you may ask, I mean, you can get this parameter sharing matrix using the procedure that I described at the beginning. But the question is, what does this do? What does multiplication by this matrix do? If we have an input interaction matrix, like patient gene matrix, suppose it is this blue grid here, multiplication by this matrix, what it does, you can think of it as first doing pooling over rows, pooling over columns, pooling over both rows and columns, and no pooling at all. And associate each of those with a different parameter, W0, W1 to W3, and then do broadcasting as necessary. So it is similar to the model that we had for set, right? Except that we have more parameters.
Can I ask a quick question on this slide?
Sure. Yeah.
There's somehow an intrinsic size with the green kind of box that you're showing, right? In terms of the weight sharing. Is that,
so
can I understand the size somehow?
This size, the size of this parameter sharing matrix, the matrix is NM by NM, right? So this original input matrix, you need to first vectorize it, right? So this is the matrix X. If you vectorize this, and you then multiply that vector by this parameter sharing matrix W, and then you unvectorize it, then the resulting operation is like this, that it's as if you're first doing the pooling, you're multiplying it with the green elements, you're multiplying the diagonal elements with it.
I guess my question is as follows, in the sense that you have, say, something like a 12 by 12 matrix, as if it looks like here, and you seem to single out these 4 by 4 blocks effectively.
Right. So the size of this one parameter sharing matrix does not match the size of this example. This example here, I have a matrix that is 7 by 7. So if I wanted to draw the parameter sharing matrix for this, it would be a 49 by 49 matrix.
Okay.
That would be multiplied by the vectorized version of this matrix here.
Okay.
Does it make sense? So the complication here is that our input in its original form itself is a matrix, and we're talking also about a weight matrix.
Yeah.
But although it is in the original form a matrix, we can vectorize it without any problem, right?
Yeah.
And then multiply it by that matrix and then unvectorize it. And then if we do that, these operations here, they have a nice interpretation. They are basically doing these pool broadcast operations.
Okay, good. So I see. So my takeaway is that there's not something special about the 4 in that. I mean, that's more like a, if I go through the algebra,
it falls out of this basically the way the parameter sharing is done.
Yeah.
And you can show that these are the only operations you can do.
Yeah.
There's no more expressive equivariant map under these symmetry constraints. And then if you just use a stack of these equivariant layers, that is, you built the equivariant NLP of these types of layers, we applied it to a recommendation system where we wanted to do matrix completion. And at the time, we got a state-of-the-art results on some benchmarks. So it performed well despite being very simple. It's just an equivariant NLP. More generally, we have the direct product of groups, 2 groups, G and G prime, and they're acting on Cartesian product of sets. So I have one feed-forward layer here, where G is acting on X, G is acting on Y is the output, and I have the corresponding equivariant map W. And I have another one for G prime. And the fact that they have the same color here, yellow, means that the same group element is acting on both input and output. Now, what we're interested in is building this equivariant map for this new setup, right? Where we have the G acting on rows and G prime acting on columns. you can show that I don't know if you can see this side of the screen. Do they have the zoom on this side? Can you see it? Can you see this side of the screen, or is it blocked?
Yeah, I can see it. Yeah.
Great. So W for this direct product structure is a tensor product of W and W prime. So in the sense that any W that is equivariant to this group action on the product space will have this form. So let's see an example. So the most well-known example, not in this, not using this derivation, but the one that you're familiar with, is 2D convolution. So if you look at the tensor product of 1D convolution matrices, these are 1D convolution, circular convolution matrices. You get a matrix that corresponds to 2D convolution. Corresponds to 2D convolution. That is, this is equivariant to horizontal and vertical translations. But it also corresponds to having a full convolution kernel. It's a very dense layer. In practice, you use local kernels for your convolution, which correspond to the sparse version of this matrix. But you can still show that this layer is still exactly equivariant to the group that we want. The other example is the one that we saw at the beginning. This is, if we look at the Kronecker product of parameter sharing matrices for set, the two parameter model that we saw for set, the Kronecker product is going to give us the parameter sharing for interactions across sets. So you have two parameters, 4 parameters. And we can repeat that for to build parameter sharing for higher order interactions. So this setup of direct product was also studied in a more recent paper by Moran et al., where they showed the universality of the resulting architecture as well when one of the structures is a set. So basically the result also shows that the model that we have here for interactions across sets is a universal approximator. Okay, so that was direct product. Now let's look at a more complicated setup. This is the diagonal action of a group. So the motivating example is that we want to look at interactions within a set of objects. So we have a graph, right? An example of this is a graph, and we want to look at the interactions of the nodes. And we can do that by looking at the adjacency matrix. The difference with what we had before is that now the same group is being applied to the rows and columns. In this case, Moran et al. Show that instead of 4 parameter matrix that we got, they get 15 parameter model. I mean, they don't present the work as parameter sharing using the parameter sharing formalism, but you can get the parameter sharing matrix with it as well. And it looks like this. So we built on that work and we looked at, for example, node edge instance matrices. In this case, you have arbitrary permutations of the nodes, and the permutation of edges is sort of dictated by the permutation of the nodes. So it's still the same group that is acting on the edges, it's just a different action of the same group member. And in this case, we got a 7 parameter model. So what we did, we noticed that we can do this basically, you can play this game with a lot of more interesting and complicated geometric objects. You can look at simplicial complexes, you can look at polytopes, and in each case you can build incidence matrices, for example, face incidence matrices or face node edge incidence matrices, the tensors. You can build these incidence tensors of arbitrary order, depending on what data you have, on how much processing power you have. And so we try to characterize the equivariant linear maps for this general setup. So this action of the group on product spaces is different from what we had for direct product of groups. In this case, we have a group that is now simultaneously transforming X and X prime, simultaneously transforming the product space. And the question is now, can we reduce the equivariant linear map in this case to the simpler ones, like we did for the direct product of the groups? The answer is yes, but it's more complicated. It's more involved. So the key observation here is that this product space that we built, it decomposes into orbits, like in the G set, where by orbit we mean that the action of the group can move any element to any other element inside one orbit, but it can't move elements across the orbits. So one important bit of information here is this decomposition. Can we characterize this decomposition of the product space to these orbits? And the answer is yes. It was given by the early works of Burnside's using Burnside's table of marks. So I'm not going to go into details about this right now, but if you have a question, I can answer that. But you basically, what this allows you to do is to, given a group acting on some sets, it allows you to figure out what would the decomposition of the group look like if it acted on product of those sets. And now once we have this decomposition of this set to the product structure, we can then look at the equivariant maps between these individual orbits. These are these building blocks, basically. So the equivariant linear map is going to decompose into these blocks. We'll have these block structures mapping these orbits. Let's see an example. So let's go back to the graph again. This is the adjacency matrix of the graph, right? It decomposes into two orbits, the elements on the diagonal and the elements off the diagonal. The reason is that if you pick an element on the diagonal, you apply any shuffling to the rows and columns, the element will stay on the diagonal because you're applying the same shuffling to the rows and columns. If you pick an element off diagonal, then you can move it to any other element off the diagonal using some shuffling of the rows and columns. So we have two orbits. At the input, we have the 15-parameter equivariant map that maps the adjacency matrix to this feature map. And our claim is that this map should decompose into maps between these orbits. And that is indeed what happens. So if you look at the map between off diagonals and off diagonals, we recover what we had for incidence matrices. We get 7 parameter. If you look at the map that goes from diagonals to diagonals, we get the 2-parameter model for the set, because we're looking at a set of nodes here. And then we can have the maps between the diagonals and off diagonals, and if we sum them up, you get the 15-parameter model.
So I have a question. Can you go back? Could
Sure.
you explain a little bit more where the number 2, 2 times 3, and 7 come from?
Sure. So the 2 here is the 2-parameter model for set. It's basically, we're looking at all the maps that go from the diagonal to the diagonal, and they are equivariant to the action of the symmetric group on the rows and columns here, right? All the maps. So we're looking at the corresponding action basically on the diagonal only. And this action is going to be just a shuffling of the diagonal elements, right? So the equivariant map should be the same as the equivariant map we had for set, which was a 2-parameter model. The 7-parameter model, because it's looking at off diagonals, it is basically only looking at edge properties. The model that we had for node edge incidence matrix could also only encode edge attributes, and that's why they end up having the same number of parameters, 7 parameters. The way we actually get these number of parameters here, you can get it using Burnside's table of mark again, but we get these empirically by running the the parameter sharing code to see what the linear move looks like. So there are both, you can get it both analytically and computationally. Did that answer your question?
Yes, thank you.
Yeah, so there is no additional secret sauce here. It's just that we know it decomposes into orbits, and we're looking to see how each map between the orbits looks like. Okay. So another utility of product spaces is in building universal MLPs. So here, the idea is that if this was your original hidden layer, you had 4 units, and then the group was acting on those 4 units, you can build the higher order hidden layer like this by looking at the tensor product of these, by looking at the product of these layers, and then having the groups act simultaneously on these different dimensions. And then you look at the corresponding high order MLP. What is important about these MLPs is that we can show that if the order is big enough, this is going to be universal approximator of equivariant functions for any group. So for any group, if this order is at least n log n, where n is the number of units, of course, this is a really large order. It's not really a practical architecture, but it guarantees universal equivariance. You can approximate any equivariant function, any continuous equivariant function up to an arbitrary accuracy. For specific groups, like for example, for the symmetric groups, which we use for equivariant graph networks, right? You can get tighter bounds. You can show that order n is enough for universality. And to my knowledge, these are the tightest bounds for the general case and for the graph networks. So the question is, how do we get these? Where does it come from? So the idea is that this high order hidden layer decomposes into orbits, like we said. And you can show us the order is large enough. There is one of the orbits here that is going to be a regular orbit, meaning that it's basically isomorphic to the group itself. And we have a separate result that says if you have a regular orbit, if you have a hidden layer that is regular, that's enough for universality. So basically, the universality of high order is due to having a regular orbit, and because we know regular orbit is enough for universality. Yeah, so that's another place where people have looked at high order hidden layers because it had a role in establishing universality.
Can I ask a question about that?
Sure.
So when in these MLPs that are universal approximators for any group, do you need to have a nonlinear activation function?
Yes.
And if so, like, how do you choose the nonlinear activation function to be compatible with the action of the group?
Right. So the proof basically relies, the proof for the regular case relies on the universality of the ordinary MLPs. Basically, what you do is that you can show that having a regular hidden layer is the same as performing all the data augmentations possible with the input and output. And because if you do all of those data augmentations, you can show universality in that case, because it follows from universality of just ordinary MLP, you get universality of the equivariant MLP. So for the ordinary MLP, the condition I believe is that you just don't want the activation function to be a polynomial function. And that's the only condition. So sigmoid is fine. Like logistic function is okay. And I think value should be okay. So there's not a lot of constraints there. And this is universality for just having a single hidden layer. You don't need it to make it a deep network. But these are not practical architectures because this order n here is really, really large. And it's just good for theory at least. At least you know there is a bound here that guarantees universality.
Thank you.
All right. So next, look at Reith product of groups. I don't have time. Okay, good. Next, I look at the Reith product of groups and how we can use it to build models for hierarchical structures. So let's motivate this. Suppose you have data from diffusion tensor imaging. You can interpret this as a set of sequences. You have a set of fiber bundles, and then each bundle is a sequence of 3D coordinates. How do you build a model for this? Or you have multi-resolution mesh data. Suppose you can have a model for mesh, say using incidence structures, and you have higher and higher resolutions. Or you have a hierarchy in the form, you want to model a document as a hierarchical structure where you have sentences and then words and then characters as nested sequences. You can do the same thing with music. So how do you build models for these hierarchies? So first, to formalize the actual data structure, we're assuming that we have a group that is acting on a set X, and then for each element of this set itself is a set, and then we have another group that is acting independently on these subsets. So here we notice we have different colors, right? It means that we have independent transformations of these subsets. And you can just repeat this over and over again to build deeper hierarchies. And this notion of this type of group action can be formalized using the Reith product. The sign here that you see here is the Reith product of G and G prime. So now we're interested in building equivariant linear maps. To just express the hierarchy in another way, we're looking here at two levels of hierarchy. G here is acting on rows, and independent G primes are acting on columns. This is the difference with the direct product. Direct product, we have just one G prime acting on columns. Here we have independent G primes acting on columns. And the same thing is happening at the output. And we want to find the equivariant linear map. What we show is that the equivariant linear map here looks like this. That is, we can build it by looking at equivariant linear maps for G and G prime separately. And in fact, you can show any equivariant linear map for the hierarchical structure as this one. So let's understand this map through an example. Suppose we're looking at the data structure we're interested in is a sequence of sequences. The equivariant linear map for sequence is this convolution matrix that we saw before, right? And the same for W prime. I want to create this W Reith. So the first term here is a Kronecker product of W with a constant matrix. It's simply blowing up this original matrix. The second term is a Kronecker product of identity and W prime. It's putting W prime blocks on the diagonal. And so we are looking at a sum of these two terms, but it's hard to see what this is doing. So this is going to be our equivariant linear map, but what is this equivariant linear map is doing? If we look at the efficient implementation of this, it also gives us an intuition. So this, this first map applied to a sequence of sequences. So here we have a sequence of length 4 of sequences of length 3, for example. This first map, if you multiply it with this sequence of sequences, what it's really doing is doing a pooling over the inner sequence. It applies the original convolution matrix, and then it broadcasts the results back to the sequence of sequences. The second one is directly applying applying separate convolutions to the inner sequences. And so we have contribution from both of these terms to the hierarchy, to the equivariant map for the hierarchy. So we can express it through pool broadcast operations and then original equivariant maps at 2 levels of the hierarchy. So we'll see what it does if you look at multi-resolution image processing. You apply this type of layer, you can assume that you have image patches, right? And then you want translation symmetry within the image patches, independent translation symmetry within the patches, and you want to also have translation symmetry of the patches themselves. And if you assume that sort of symmetry, sort of hierarchical symmetry, you naturally get pooling over image patches that people use. So basically what you need to do for just one layer is to pool over these image patches, apply convolution, and then broadcast back. In practice, you don't see this broadcast back in a lot of image processing architectures because we're more interested in building invariant networks rather than equivariant networks. So when you build an equivariant network, you have to also broadcast results back within one layer. Okay, so in practice, we applied this segmentation of point cloud data, large point cloud data, and the way we did it was that we artificially created these block structures, these voxels. And then we said, let's say that these voxels have translation symmetry, and the points within the voxels have permutation symmetry. So we have a hierarchy of translation and permutation. And if we now build the equivariant linear map for this, using the hierarchy in these pool broadcast operations, we saw that it performed really well in practice. So this is application of this model to point cloud segmentation of very large point clouds, where we got good results. So different data sets. The model performed well. So at this point, it's useful to compare these 3 different models for the example of symmetric groups. We saw the direct product, right? We said that it's modeling the interactions across 2 sets. The model had 4 parameters. We built it using tensor product. We looked at the diagonal action. We said that it's modeling the interactions within a set, in this case, set of nodes for a graph. And we said it has 15 parameters. And we can create these 15 parameters by looking at the equivariant maps between the orbits. And then we can look at the wreath product. This can model nested sets. So we have sets within sets. When we build an equivariant map for that, you get this 3-parameter model. And we can build it using the procedure that we saw. And in the paper, we give more examples of different ways of combining equivariant maps for sets and sequences and contrasting what you get for product versus direct product versus wreath product. Okay, so the final type of composition that I look at is the block system. This is a generalization of hierarchy, but I'll look at it in the context of one particular application. So this application is a spherical data. It's very motivated in physics and astronomy, in earth and atmospheric sciences. You look at climate data, or you look at the images from omnidirectional camera. We have a spherical sequence. And one common way of modeling spherical data is to pixelize a platonic solid. And the choice of platonic solids is because these are highly symmetric. These these solids are face, edge, vertex transitive. That is, you can move any vertex to any other vertex, or any face to any other face. And these are the only ones that have that property. They're very useful in approximating the symmetries of the sphere. So the way like people use this is that they try to recursively subdivide each face into smaller faces and then project that to the sphere. So if you do that over and over again, you get a shape that looks like a sphere, like it becomes more and more like a sphere. Now, to build an equivariant map that can operate on these objects, we need to define their symmetries, right? If we were working with a sphere, we would know what symmetry we could work with. We could work with SO3, but now here, because of this pixelization, there is no subgroup of SO3 that transitively acts on these pixelizations. So that's a big problem in dealing with pixelizations of the sphere. So one solution is the following. We can just pick each face, say that we have translation and rotation symmetry on that face, and then say we have a set of faces. So we have a hierarchical structure. We have symmetric group on top because we have a set, and then we have translation and rotation symmetry in each face. So this model is very similar to what gauge equivariant CNNs do for pixelized spheres. Even better, we can have a hierarchy, but this time instead of the symmetric group on top, we can use the symmetries of the actual solid. So these symmetries are well known, and we can replace the symmetric group with the symmetries of the solid. So each faces have these high-level symmetries, and then within each face we have translation and rotation symmetry. But there's a problem with this. The problem is that we're assuming that you can rotate each face independently, while in reality we know that the rotation of each face follows from the rotation of the solid. If I can't just rotate the solid one way and then rotate the faces independently of each other. So it seems like we have a hierarchy, but at the same time we have a constraint between the two levels of the hierarchy. That is, the rotation of the solid at the top level is going to dictate something about the transformations at the lower level of the hierarchy, which is the rotation of each face. It doesn't affect the translation, but it does affect the rotation of each face. And we can formalize these using block systems in permutation groups. The general idea of block system is that you can partition the G set into subsets such that these subsets are invariant under the action of the group, meaning that if two elements belong to one subset, they're going to stay in the same subset after any transformation by G. That is, any transformation, any permutation within that group either does not move the block, or if it moves the block, it moves all the elements, like it either moves all the elements inside the block to some other block, or just shuffles elements inside the block, or does both of these at the same time. It doesn't separate the elements inside the block. And there is a rich theory on block systems. There is a correspondence between these systems of blocks and the overgroups of the stabilizer in the group action. So you can basically build on that theory. This generalizes hierarchy in the sense that hierarchy is a special case where we have a separate transformations of the block and stuff within the blocks, while these two could be tied together. And this gives us a way to have interactions within the two levels of the hierarchy. And so we use this formalism to define the symmetry group in this case. And once we've defined the symmetry group, we can then derive the equivariant linear map for spherical signals. And so one thing we should do then is to compare these different models. The model that we built by looking at a set of symmetric elements, the set of faces where each face has translation and rotation symmetry, the model where instead of set, we use the symmetries of the solid itself. This is the orange one, and the one where we use a block system. So in each case, we are restricting the symmetry group more and more. And we build these models for spherical MNIST data. This is MNIST projected to the surface of the sphere using different types of pixelization, using cube, tetrahedron, octahedron, etc. And what we see is that as we constrain the symmetry group, the performance improves. And if you look at in comparison of this model with other methods on a spherical MNIST, we are competitive. On bigger data sets, we outperform the state of the art by a large margin. So if you look at the omnidirectional camera image segmentation, Stanford 2D, 3D data set, we get much better results than the existing methods. And the same is true for semantic segmentation of the climate data. So here again, model for Cube is very scalable and it performs really well in practice. So in summary, talked about equivariance as a way of biasing deep models to make them more sample efficient based on our prior knowledge about the symmetries of the task. And we've seen how to encode this equivariance to particular permutation groups into multilayer perceptrons. And then we looked at different types of composition and their utility. So we considered the Cartesian product of spaces. And then we said, let's say if the direct product of two groups is going to act in that Cartesian product of spaces, if we have a diagonal action, if we have a hierarchy, or if we have a block system. So all of these are acting on that Cartesian product of spaces. This block system could also be used to formalize semi-direct product. I did not talk about that. So for semi-direct product, we can also get the parameter sharing matrices. And we did that for the application and for spherical signal processing. And there are actually more complicated setups where we can use compositionality. We can have a complex combination of union of domains, product of domains, and groups acting on them. And composition of groups, again, product of groups acting on them. And so I'll leave that and formalization of that future work. Thank you very much, and thanks to my collaborator. These are the papers that I discussed in this talk. Maybe I should read the name of my collaborators, but maybe you can do that too.
Yeah, thank you very much for this very interesting talk.
Thank you.
Are there questions? While people get ready with their questions, I can ask one. So when you had the universal approximation result, you had this kind of large N versus D kind of statement. Is there somewhere where you actually can see an effect of, if you don't go to large enough N? Is there something, where you empirically see something, or is there...
Yeah, so intuitively, like take the model for set. Right? For set data, you have an input that is a vector, and you're assuming exchangeability of the input. So you have the symmetry group acting on the input. On the hidden layer, you can have a matrix of hidden units, right? If you have a matrix of hidden units, or you can have a vector like the set model that we saw, the deep sets model. If you go to the matrix model, for example, what you're doing is that model is now looking explicitly on pairwise interactions of the elements of the set. But if you just go with a vector, that's not explicitly modeling pairwise interactions. So it's obvious that this second order model is now going to be more powerful. And in fact, you can show that there is a hierarchy of expressivity for models based on the subgroup relation of the stabilizer. So if you build the lattice structure of the stabilizer subgroups, the same lattice structure can be used to show that one type of layer is going to be necessarily more powerful than the other type of layer. The same thing would follow from having higher order layers. So yeah, you can show that one can basically do whatever the other one can do, but that's not too much. That's not a very strong statement. And intuitively, it's what I said. Like you can look at the set model and you see that it is now looking at higher order interactions.
What's the reference for that? Sorry, can you give the reference for the statement?
So no, I haven't written it. So there is a quick discussion of that in this paper. Well, discussion of material related to this is in this paper. But so here, I'll tell you the idea. So you have suppose you have two G sets. The stabilizer subgroup in one of those G sets, in both of them, you have the same group. G is acting on two sets. In one of them, the stabilizer subgroup is an overgroup of the other. So what you can do is that you can show that, so both of these correspond to quotient spaces, but one of them contains the other one, strictly contains the other one. And so you can show that any function, any linear map that you can define through one of these, you can also define through the other one by just doing pooling over all the elements in the same what do you call it? The same subset belonging to the same quotient. So the proof is not difficult, and I thought it was sort of not a lot of value added, so I didn't include it in this paper, but you can actually show that. It's also intuitive, like take the group action take the action of symmetry group on a set Sn on a set of size n. The stabilizer subgroup in that case is Sn minus 1. Okay, so basically you're saying the group that stabilizes this node is a group that can permute all the other nodes. That's why Sn minus 1. But if you go to the second order model, the stabilizer group is Sn minus 2. And so in one case, the stabilizer is a subgroup of the other one. And you can show the second order model is strictly more powerful than the first order, because in addition to the first order stuff, it's also looking at the interactions of the nodes. So that's as an intuitive example. But this is a general statement you can make about any group, any permutation.
Thank you.
Any more questions?
Very nice talk. I started digging a little bit into your paper as it was going on, this universality paper. I was curious, there's this limit that a lot of people study with the infinite width limit where you have neural networks drawn from a Gaussian process. But it seems like if you tried to extend that to this G invariant case that your theorem applies to, you might run into an issue just because even as the number of parameters becomes infinite, and you would normally have a GP in that context, the number of orbits doesn't necessarily go to infinity. Have you thought much about sort of getting various different handles of statistical control over the infinite limit in these cases?
No, not really. So the trick that I used, basically what the proof relies on in that paper for universality, is very simple. I mean, the results that you get is wide. You get results that are, the bounds that you get for the order is tight, but the proof, the proof technique is very simple. We're simply saying, we're simply showing first the proof for the having a regular hidden layer, right? I don't know even what happens. So for the infinite case, it's much, I think it's very different. You need different ways of thinking about these, because in this case, the universality is following from the fact that the regular layer is applying all the transformations in the group. For the, I mean, effectively, it doesn't really do all transformation, but it is as if it is doing all the transformations in the group. But for the case of, if you have infinite group, then that can't be, right? So this type of technique can't work. You couldn't be applying all the transformation in infinite set. So I'm not sure what's the right way to think about it when dealing with infinite.
I see. So I mean, what I would want to say is that it just seems like in this context, the way that you're talking about the finite groups and large N interplaying in this context simply makes it hard to have enough independently drawn weights at large N to be able to have a Gaussian limit.
Oh, I see what you're saying now.
Because large N is helping the approximation in the standard context, but in standard contexts that aren't related to symmetry, large N is also related to becoming Gaussian, which is coming from having enough independent draws of the parameters. But
Right.
I think it's exactly the weight sharing that's sort of obstructing that Gaussian. Well, at least naively, it seems to me that the weight sharing is obstructing the Gaussianity in the large N limit, even if large N is helping the approximator, which I think is what you're saying, right?
Right. So I think there should be two regimes there. Now that you mention it, the effect of the number of parameters. There are equivariant linear maps in which the number of parameters grows with the group, grows with the domain size, and the ones in which the number of parameters are going to stay the same regardless of the size of the domain. For example, the set model or the graph model, the number of parameters stays the same even if you work with a much bigger set or much bigger graph. But for convolution layer, if you don't use local filters, the actual number of parameters that you have, it can grow with the size of the image that you're dealing with, because you can have bigger and bigger filters. So if the number of parameters grows with the size of the domain, maybe you don't have that problem. And so maybe still you can do similar sort of analysis.
Right.
But if it grows, you could still have multiple channels to deal with that. So the analog of having more units for an MLP is having more channels.
Yes.
In an equivariant MLP.
Absolutely. Yes.
So, but I haven't really thought about it.
Well, it just seems like an interesting.
Yeah.
Yeah, I mean, you're right. The name of the game does change if you change the dimension of the domain, and that's sort of standard in these Gaussian contexts. So, for instance, if the size of the domain grows, typically you have Gaussian pre-activations. But as far as the network outputs themselves are concerned, it's usually you usually fix the domain size and then take the hidden layer to infinity. But I don't know. It was a little bit off. It was a little bit off the cuff, but famously, there's multiple different ways in which large N gets null, and you're taking this classic universal approximation and applying it in the G invariant and G equivariant cases. But
right. So I think what you're saying, the setup that you have in mind would be possible by having even the same actions on input and output and the input and the hidden layer, but then just taking the limit of the number of channels to infinity. So that would have similar effect, I think.
Yeah, and
it would be harder to run with.
Right, and I mean, in your paper, I think you also do the single layer case independent of any convolutions, and then it actually is the width, I guess, right?
Yeah. So in our case, we actually do need we may need arbitrary number of channels. It's the same as if, you know, in the MLPs, the universality doesn't come with a bound on the number of hidden units. This is going to translate to the number of channels in that case.
Good. Can I actually ask another line of questioning, if you don't mind? I don't know if other people have questions.
Yeah.
So another thing that would be natural to a physicist is to, when you consider symmetry and universality and approximators together in the same breath, like you're doing, to not fix the symmetry and allow for error in the function itself, but potentially allow some little bit of symmetry breaking as well. Have you thought about that in this context? So sort of having it be equivariant up to some small equivariance error.
Right. Yeah. No, that's a very interesting setup. And I've actually heard that before. People, I think somebody should be doing this, but this framework is not going to allow that. This is very rigid in the sense that we should know the group, we should know the action, and we are just enforcing this off the bat on each layer. Ideally, what we want is that to learn. I mean, the next step would be not to know the action, but know the group, or even not to know the group and be able to learn that and enforce that. There are some works that are coming out in that area too, so it is sort of active. But what you're saying is another type of problem, again, in a somewhat more relaxed family where you want to allow for a bigger group acting.
Yeah, I'd be curious if you allow for a second error parameter, one related to symmetry rather than accuracy, if that potentially allows you to.
So you would have one layer for one symmetry group. You would have another feed-forward layer for a different symmetry group, maybe a bigger one, and then or have just an ordinary MLP and have them both.
Yeah, I guess I hadn't thought about how I would necessarily engineer the architecture, but
yeah.
I guess
yeah, it is an interesting problem to look at, but I don't have
cases where you have an approximately invariant function where the error is bounded by some parameter that you could potentially take to be small, and then in the same way that we consider error in the accuracy related to a universal approximator, making the notion of symmetry approximate too is, I guess,
yeah. So that is something we have done something about it. It is on review, but so this is different, I think, from what from the previous setup where you were allowing for a bigger group maybe to act or to be equivariant to maybe a bigger group. So in this case, you could say that I want to impose equivariance not through the imposing some constraint on the architecture, but I want to impose it through some objectives, so that if it is not satisfied completely, if the objective is not optimized perfectly, still there is equivariance to some extent. So I'd say stay tuned for that.
Cool.
And something along that lines.
Very good. Well, very thanks for the talk and the very beautiful set of works. I don't think I had seen your universal equivariant MLP paper. It's very nice. So.
Yeah, it's a very it's more on the theory side as well. Thank you.
We like that direction. So thank you.
Any further questions? I cannot see any urgent ones coming up. So thank you very much again for a very nice talk, and I'm going to stop the recording now.
Thank you very much.